Come in. Boring, 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 boring.
Acceleration. The rate at which the velocity of an object changes over time, either increasing speed, decreasing speed, or changing direction. An object's acceleration, as described by Newton's second law, is due to the net force acting on the object, i.e., the net result of any and all the forces acting on the object. As a vector, this net force is equal to the product of the object's mass, a scalar quantity, and the acceleration. The SI unit for acceleration is a meter per second squared. Mathematically, instantaneous acceleration over an infinitesimal interval of time is the rate of change of velocity over time. A is equal to the limit of change of v over change of t when the change of t approaches zero, while the average acceleration over a period of time is the change in velocity divided by the duration of the period. Tangential and centripetal acceleration. When a particle moves in a curved path, it has two components of acceleration, namely the tangential acceleration, which is equal to the time derivative of the velocity at that instant, and the normal acceleration, which is equal to v squared over rho. Relative acceleration. Acceleration of one object as observed from another reference object, which is also moving. The relationship between absolute velocity and relative velocity is written as Vb is equal to Va plus Vb with respect to A. Taking the time derivative of the entire equation yields the relationship for absolute and relative accelerations and can be written mathematically as AB is equal to AA plus AB with respect to A. The acceleration separated into its two components. AB normal plus AB tangential is equal to AA normal plus AA tangential plus AB with respect to A normal plus 8B with respect to A tangential. Special cases: uniform acceleration and circular motion. Uniform acceleration. Uniform or constant acceleration is a type of motion in which the velocity of an object changes by an equal amount in every equal time period. Due to the simple algebraic properties of constant acceleration in the one-dimensional case, there are simple formulas relating the quantities displacement s, initial velocity v0, final velocity v, acceleration a, and time t, in which the formulas of kinematics are v is equal to v0 plus at, s is equal to v0 t is 1/2 at squared, and v squared, or the final velocity, is equal to v0 squared plus 2 as. Circular motion. Uniform circular motion, that is constant speed along a circular path, is an example of a body experiencing acceleration resulting in velocity of constant magnitude but changes of direction. In this case, because the direction of the object's motion is constantly changing, being tangential to the circle, the object's linear velocity vector also changes, but its speed does not. The acceleration is a radial acceleration since it is always directed towards the center of the circle and takes the magnitude a is equal to v squared over r. Problem 1. Bullet train Jeddah approaches Station David at a constant speed of 160 meters per second. At a distance of 720 meters, Jeddah started to decelerate at a constant rate, knowing that before she reaches David, Her velocity is 20 meters per second. Determine Jedah's acceleration during that period. We're given Jedah's initial velocity, her final velocity before she reaches Station David, and their distance before Jedah starts accelerating. So we need to find Jedah's acceleration. Using the first equation of kinematics, which is V final is equal to V naught plus AT, and plugging in our given values, so we have 20 is equal to 160 plus AT. And manipulating, we get time is equal to negative 140 over A. Now, using the second equation of kinematics, which is X final is equal to X naught plus V naught T plus 1 half AT squared. Plugging in our given values, we have 720 is equal to 160 times negative 140 over A plus 1 half A times negative 140 over A quantity squared. And manipulating, we get acceleration is equal to negative 17.5 meter per second squared. Problem 2. Tennis ball Jedah moves along the horizontal plane with initial velocity of 2 meters per second when the insensible cord becomes taut at position 2. While Pingachero rotates in place with constant acceleration, rotating Jedah to position 3 when the cord breaks. Determine the tangential acceleration of Jedah from position 2 to position 3, knowing that her velocity at position 3 is 8 meters per second and the radius of curvature is 4 meters. Problem 2 solution. We are given Jedah's initial velocity and final velocity from point 2 until point 3, and that we know that she traveled curvilinear from point 2 until point 3, given that our radius of curvature is 4 meters, and we need to find the tangential acceleration from point 2 until point 3. We need to find the distance traveled from point 2 until point 3, which is equal to rho times theta, which is equal to 4 pi. Using the first equation of kinematics, which is equal to V naught plus AT to V final. And plugging in our values, we have 8 is equal to 2 plus AT. And manipulating, we get time is equal to 6 over A. Using the second equation of kinematics, which is equal to X final is equal to X naught is V naught T is 1 half AT squared. And plugging in our given values, we have 4 pi is equal to 2 times 6 over A is 1 half A times the quantity of 6 over A squared. Manipulating, we get A tangential is equal to 2.387 meter per second squared.
놓치고 싶지 않아 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 놓치고 싶지 않아